Welcome to Lecture 5, Section 1. This PowerPoint will introduce you the Laplace transform for use in this course. In Lecture 4, we talked about dynamic process control and used a fluid heater as an example. We set up and solved an ordinary differential equation to describe the outlet fluid temperature. We used proportional control and neglected the sensor, feedback element, and actuator. We were able to solve the equation analytically. But in a complete closed-loop control system with all the elements would be much more complex, beyond what we can handle analytically. And industrial processes are even more complex. The complexity of real systems is what is motivating us to learn about Laplace transforms. In this lecture, we assume that you don't have any experience with Laplace transforms. Laplace transform is a tool for solving ordinary differential equations. Differential equations are equations with one variable and derivatives with respect to time. We need to use differential equations because dynamic process change with time, and so some of the process variables will vary and have derivatives with respect to time. We use Laplace transforms as a tool or method of analysis, but we will not get into the theory about Laplace transform. And you will use Laplace transform in a cookbook fashion. The term transforms in the name Laplace transform suggests that we will take an ordinary differential equation and transform it. Then we will manipulate the transformed Laplace equation to put it into a form that will be useful to us so that we can take the inverse. One way to think about this transformation, manipulation, and inverse process is to remember that the differential equations we start with describes a physical system in the time domain. After we transform this time domain equation into a Laplace expression, we have an expression in terms of frequency in the Laplace domain. If you have troubles grasping what a Laplace expression in terms of frequency means, don't worry about it. We won't be concerned about what it means. After transforming the differential equation onto the Laplace domain, we will manipulate the equation as needed using algebra before we take the inverse. And taking the inverse of the equation in the Laplace domain transforms the equation in terms of frequency back into an expression in the time domain with the original physical meaning. So the Laplace transform is a middle step. For our cookbook approach, we start with an ordinary differential equation that describes one of our dynamic processes, heating a fluid, liquid, level in a tank, flow from a tank, mixing without reaction, or a bioreactor. These expressions will have the time-dependent terms and derivatives. First, we take the Laplace transform. This transforms the ordinary differential equation ft with its physical meaning into a Laplace expression in the Laplace domain. Then, in the Laplace domain, we use algebra to reorganize the Laplace expression to solve for Fs. After solving for Fs, we will take the inverse of the Laplace expression and transform it back into a time-dependent expression Ft that no longer has the derivatives. Before we get into the details of Laplace transforms, another concept to introduce here is transfer functions. Transfer functions are mathematical expressions that relate an input function to the output function. Transfer functions are defined as the ratio of the output function over the input function. Sometimes transfer functions are defined as the ratio of the response function over the forcing function. This is simply using different terminologies, where the input function is the same as the forcing function and the output function is the same as the response function. Transfer functions can be illustrated using a block diagram, where the input functions enter the transfer function block G and produces the output function. We will spend an entire class talking about transfer functions later in the semester. We introduce them here because in the Laplace domain, ordinary differential equations can be simplified into transfer functions that relate the input function to the output function. As a matter of fact, we will find later that we can take a complex control system with multiple transfer functions describing multiple control loops and elements and combine it into one overall transfer function. We won't do that until we get near to the end of the semester, though. So transfer functions are important concepts in process control. Here is the mathematical definition of a Laplace transform. We will never solve this integral. That portion of the expression is only given for completeness. We start with the function of time ft in the time domain. Be sure to note that we will always assume that ft equals 0 for time t less than 0. Later in the semester, we sometimes have to rewrite the equation if ft does not equal to 0 at time less than 0. The script L is the notation used to indicate that we are taking the Laplace transform of the time domain expression ft. We will use the capital F of f's to represent the Laplace transform of ft in the Laplace domain, which is the frequency domain. The small s represents a complex variable in the Laplace domain. Finally, be sure to note that fs has no information at t less than 0 because it is not defined at t smaller than 0. So in process control, things start at time equals 0, and we say that we have no information prior to time equal to 0. At this point, I would like to have you look at the table on page 5-5 and 5-6 in the course packet. This is a Laplace transform table. We will use this table and MATLAB to transform time domain expressions into Laplace domain expressions, and then take the inverse transforming to transfer back to the time domain. The Laplace transform table has 3 columns. Column 1 gives the equation number. This is simply a way to reference which equation or row in the table used. The middle column gives time domain equations, and the last column, the third column, gives the Laplace transform of the time domain equation in the middle column. I will explain how to use the table in Lecture 5, Section 2, when we go over some examples there. There are 33 equations in the table, and some of the functions have brief descriptions. We will use the table starting in the middle column to convert terms in our ordinary differential equation into the corresponding Laplace domain terms in the third column. Later, after solving for fs in the Laplace domain, we will use the table to convert the Laplace terms back into time domain terms. We will look for the corresponding terms in the third column to find which equation to use. In the Laplace transform table, equation 1 tells us that ft in the time domain equals fs in the Laplace domain. Equation 2 tells us that the sum of two functions that are added together in the time domain are equal to the sum of the equivalent Laplace domain functions added together. Equation 3 tells us that multiplying a time domain function by a constant a equals the Laplace domain express fs times the constant a. Now let's talk about several important functions. They are described in Section 5 of the course packet, beginning on page 5-2. In the Laplace transformation table, we will skip to equation 6, which is a step function, with a step magnitude of a. The simple sketch shows that in the time domain, the function is equal to 0 at time smaller than 0. At time 0, we have a step change of magnitude a. The sketch shows a positive step change, but a could be negative. The Laplace transform for a step change of magnitude a is a over s. We find this in the third column of the Laplace transform table for equation 6. If a equals 1, it is called the unit step change, and the Laplace transform is 1 over s, which is equation 5. A is a constant, and it can be positive, negative, a fraction, or a decimal value. Step functions in the time domain are equal equation 5 and 6 in the Laplace transform table. Step functions in the time domain are equations 5 and 6 in the Laplace transform table. The ramp function is a times t beginning at time 0. Because the value at time 0 is 0, there is no zero offset term b. Ft equals 0 at time smaller than 0. A is a constant and is a slope of the ramp. A can be positive, negative, or a fraction. The Laplace domain expression for a ramp function of a times t is a over s squared. Again, if a equals to 1, it is called the unit ramp function, and the Laplace expression is 1 over s squared. The ramp functions correspond to equation 7 and 8 in the Laplace transform table. The Laplace transforms for sine and cosine functions are given by equations 9 and 10 in the Laplace transform table. Sine omega t equals omega over s squared plus omega squared. And cosine omega t equals s over s squared plus omega squared. Omega is a constant, and it can be either a positive or negative value. The step, ramp, and sine functions are often used as input functions of processes, and we will talk more about input functions later in the course. The exponential expression, equation 15 in the table, is a times e to the power minus alpha t in the time domain, and it equals a over s plus alpha in the Laplace domain. Both a and alpha are constants. There are numerous other time domain functions in the Laplace transform table. To transform a time domain term, find the term in the second column and write down the Laplace transform in the third column. Exams in this course are open book, so you don't need to memorize any of the Laplace transforms because you can look them up in the table. MATLAB can also be used to find Laplace transforms. These examples are on page 5-12 of the course packet. Feel free to use MATLAB on the problem sets. Let's go over a couple of other Laplace relations. Watch out for the terminology because the terms are similar, and there's more information in the course packet. The translation of transform is used when the time domain function ft is multiplied by e to the power minus alpha t. In the Laplace domain, the effect is to translate the function f by alpha, so it becomes f of s plus alpha. We will use this relation near the end of the semester to model time delays in the process. For translation of function, the Laplace domain function fs is multiplied by e to the minus alpha times t. The effect is that the function is translated by alpha in the time domain. So f of t minus alpha in the time domain equals e to the power of minus alpha x, s, in the Laplace domain. Physically, this has the effect of changing the position when time equals 0. Again, there are numerous other time domain functions in the table. To transform a time domain term, find the term in the second column and write down the Laplace transform on the third column. For Lecture 5, Section 2, we will go through some examples in the course packet. Before we do some examples, we need to talk about how to transform the derivatives in differential equations. Remember, we use ordinary differential equations to describe many processes, and we will have derivatives to transform. These are presented in the course packet on page 5-7. So if our equation has a first-order differential term with respect to time, the Laplace transform is s times the Laplace domain function fs minus the value of ft at time 0. We need to know what the function is at time 0. If we have a second order differential term, the Laplace transform is s squared times fs minus s times ft at t equals 0 minus the first derivative of f0. So we need to know f at t equal to 0 and the first derivative at time 0 to complete this transformation. These will be part of the initial conditions given in the problems. Here is the Laplace transform of a third-order derivative. Again, the initial conditions needed to give f at time at 0 and whatever derivative terms needed. This brings us to the end of Lecture 5, Section 1, in which we introduced Laplace transform. We are using Laplace transforms as a tool because they will allow us to handle more complex control systems. Please write down any questions you might come up with and bring them to class so that we can discuss.